Hello everyone, and welcome to our second video on directional derivatives. And in the first video, toward the end, we came to this conclusion: if we were looking at the function capital R of t, which was determined by taking the function little r of t and restricting the function f to that curve or that path in the xy plane, that generated a curve on the graph of the function f, which is a surface in 3 space. And the question we wanted to answer was, does the derivative of that third component, which is the height function, does that derivative represent the slope? And we came to this conclusion in the box that that derivative will equal the slope, provided that the denominator up here in this fraction, which is the length of the first derivative, exactly came out to be 1, because that's the only thing that those two quantities are off by. That is what the slope is equal to, and therefore the slope will equal only the first derivative, or the derivative of that third component, if the length of the first derivative of little r of t, the path in the xy plane, is 1. And we know from our earlier experience that that will be true if the curve little r of t is parameterized by arc length. Alright, so if we have an arc length parameterization for our curve little r of t, it will represent the slope of the surface in a specified direction, and that direction is determined by the derivative of little r of t, as discussed in video 1. Now, we're going to kind of reverse this, because that doesn't show us how to define a directional derivative. What we've just done in our previous work here is being given a vector valued function little r of t, and that helped us determine the slope of the surface, alright, in the r prime of t direction. Again, the direction of the curve little r of t, and therefore the direction that we're moving on the graph of the function f, is determined by that derivative vector little r prime. That will help us determine the slope of the surface if the curve was parameterized by arc length. What if we want to go into a different direction, some other direction other than r prime of t or r prime of 0, whatever it might be? If that's the case, we might need to find a different curve. So what we want to do is reverse the analysis that we've kind of gone through and say, how do we find the slope of the surface in an arbitrary given direction? And so, for instance, the direction determined by some vector little v in the xy plane. Alright, to do this, what we need to do is we need to come up with a curve in the xy plane that satisfies these following 3 conditions. First off, it has to point in the direction we want to point in. It has to point in the v direction. We need, therefore, its derivative at the point we're focusing on, and we're going to focus on the t value, the parameter value 0. That's just going to be the point corresponding to where we are on the graph. Alright, so it's got a point in the v direction, so the curve has to have its first derivative equal v when t is equal 0. It has to pass through the point we want to consider. Okay, so r of 0 is equal to the point ab, and that's the point we're going to plug into the function f to get the point ab, f of ab on the graph of the function. And then the third thing, it's parameterized by arc length, and therefore it has speed 1. Okay, there are many ways to come up with curves that will do that. The easiest type of curve to write the parameterization down for is a line. So that's what we're going to use. We're going to use a straight line. Alright, and we know what the vector form of a line is. Okay, the vector form of a line, I'll just put it off to the side here. L for line is going to be t times our direction vector plus our initial point vector, plus our initial vector, some vector point that lies on the line. Now, we want to use the vector AB as our starting point, and we want the direction vector to be v, which is the given vector, right, or the given direction. That's our compass direction that someone's given us. All right, now that will be good, because if I plug in 0 for t, we're going to get the vector AB. If I take the derivative with respect to t, we just get the vector v, and therefore if I plug in 0, we're going to get the vector v also. So it satisfies point number 1, condition number 1 up here, and condition number 2. How do we get it to satisfy condition number 3? Well, we've seen in our previous experience when we were creating arc length parameterizations from given parameterizations for lines, that will be the case if we just normalize the vector v. So as long as v is a non-zero vector, and that's what we're assuming, we're pointing in a direction. The zero vector does not have a specified direction, so we're assuming v is non-zero. Then all we need to do is redefine the curve by normalizing the vector v. All right, and we know how to do that. We simply take the vector v and divide it by its own length. That's what we're going to call the vector u. All right, and maybe its components are going to be u1 and u2 as usual. So we're essentially going to do a reparameterization here. I'm using the same parameter t. All right, but what is the difference between what I have starred right here and up above? The only difference is the direction vector we're using is u, not v. So it's a unit vector u, not the arbitrary direction vector. All right, so it's a scaling of the given vector direction we were given. All right, now to get past the second equal sign, all I did was distribute the t to each component and then add together. So we're talking about t times the vector u1 comma u2 plus the vector ab. If we just want to combine this, we would do the scalar multiplication and then add component wise. That gives us t times u1 in the first component, t times u2 plus b in the second component, t times u1 plus a in the first component. Now so that curve right there satisfies all three of these conditions. All right, it points in the direction we want it to. It passes through the point we want it to at the appropriate time, parameter value t equals 0, and it's parameterized by arc length. All right. Now, what do we need to do then? We can just compute the derivative of the third component, meaning the derivative of the height function. So everything we've done so far shows that the slope of the surface in the v direction, which is the same as the u direction, all right, those are pointing in the same direction, will be the derivative of that height function, f of r of t, evaluated at t equals 0. All right, now that's it. That's what the slope will equal right there. All right, now the rest of this is just evaluating it. So how do we evaluate a composition of two functions like this, where we have a function of two variables f, and it's being evaluated at another two functions x of t and y of t? All right, we can think about this on the inside as the vector little r of t there. Well, we do the gradient of the derivative of the outside function, which is the gradient, evaluated at the inside function, and then it's going to be dotted with the derivative of the outside function. Or sorry, the derivative of the inside function. All right, so that's the coming directly from the chain rule. All right, now we also then have to evaluate at t equals 0, right? That means plug in t equals 0. All right, so all I'm doing now is plugging in 0 here and here wherever we see t to get to the next line. Now when we plug 0 in for t, it's going to wipe these out. It's going to be gone. Just a in the first component, b in the second component. So that's why in the next, past the next equal sign, we just have the gradient at the point ab. When we plug t equals 0 when we get r prime of 0. But r prime of 0, the reason we cooked up this curve r of t up above here, that in the asterisk, is specifically because one of the reasons was that the derivative at 0 was equal to our given direction vector, and that now we came up with the unit vector u. All right, so r prime of 0 is equal to u. All right, so there it is. This is the definition of it. I'm going to look at the box below in a minute. This is how to compute this. All right, so you can expand this dot product, and you'll see this done in other textbooks as well. Remember, the gradient vector is equal to the partial derivative with respect to x in the first component and the partial derivative with respect to y in the second component. So if we take that dot product with the vector u, we're going to multiply the partial with respect to x times u1 plus the partial with respect to y times u2. And that's a number over here, right? Those partial derivatives are evaluated at a fixed point, and it's dotted with and multiplied by those fixed numbers. All right, so that leads us to our definition. All right, so this is how and why we should define the directional derivative of a two-variable function to be the derivative of that composition evaluated at t equals 0, assuming that derivative exists. Now, I have more in the equal sign up above, but that second or third equals came from the chain rule. All right, so there's the definition of it. Again, it's the derivative of the height function at the appropriate value of t, assuming the derivative exists. By the chain rule, though, and this is what we're going to use more often than the definition, that directional derivative will equal the gradient of f dotted with the unit vector u. The gradient of f at the point AB dotted with the unit vector u. That is a consequence of the chain rule. All right, a couple other remarks. For functions of two variables, that directional derivative does represent a slope. We tried to motivate this from something we could wrap our head around, something that we could visualize. It's going back over to Seeberger's applet. The directional derivative in this case is coming out, if you look at the top of the screen here, the directional derivative is 0.163. All right, so it's slightly positive, and notice it's pointing over here in the green vector underneath in the xy plane. It's pointing kind of into the second quadrant. We're going slightly uphill. If we moved the point, though, a little bit, then we might be going uphill or downhill at that point. All right, so same angle, a little different point. Now we're going downhill. All right, we can see the directional derivative up here is negative at the top of the screen. All right, so it's the slope. We can also think about that as the instantaneous rate of change in the direction of u. Now, the other remark here is that the directional derivative, as we've defined it, can be extended to functions of 3 variables or 4 variables or however many. We just won't be able to graph it, so we lose some of the geometric picture here. We can still interpret that, though, as the instantaneous rate of change in the u direction. So I've wrote out how we would compute, all right, the directional derivative for a 3-variable functions. It would just be a 3-variable vector u, and the gradient would be evaluated at a point, say, A, B, and C. All right, but you're still getting a numerical quantity. All right, that is going to be it for this video.